In this video, I will give an overview of how to use statistical analysis for imaging data. The motivation for using statistical analysis for imaging data is to help us find the location of distinct chemical species in a map. For instance, the image on this slide shows the location of iron oxides and iron sulfides in a uranium-bearing sediment. Statistical tools allow us to objectively identify the location of chemical species in a complex matrix. They help us to pick out where chemical changes are, as opposed simply to changes in concentration. We will focus in this tutorial first on principal component analysis. It is used widely throughout many scientific disciplines and engineering disciplines. It looks for the greatest variations in your data set, and it breaks down the experimental signal into component signals. Components are ranked based on how much of the variation within the total signal each of the component signal expresses. This is easier to understand with an example. The example shown here comes from a tutorial on principal component analysis written by Jonathan Schlens. Imagine we want to understand the motion of a ball on a spring. This ball moves back and forth in the x direction when the spring is pulled. However, we don't know in what directions the ball moves to begin with, so we randomly set up cameras in 3 dimensions to monitor its motion. In the image shown here, you can see the ball and spring in cameras A, B, and C, which are pointed in random directions. Our question is, how do we derive an equation that expresses the motion of the ball on the spring based on measurements of the ball's position taken by the randomly placed cameras? We look for the direction along which the greatest variation in the placement of the ball occurs. So let's take one camera, camera A, as an example. Camera A provides the location of the ball as a function of 2 coordinates, x of A and y of A. We select a new axis along which we will align the data such that this new axis P is aligned with the greatest variation in the data. If we were to look at the variation in the data as a function of the angle of P, we can see that we are selecting the angle of P that exhibits the greatest variation and the greatest signal to noise. This new axis P is our first principal component. In general, this is how PCA works. We select a normalized direction in m-dimensional space along which the variance in the data is maximized. We save this vector as P1. In our example, m is 6 because we have 3 cameras, A, B, and C, which each provide 2 location coordinates. We then find another direction along which the variance is maximized. PCA includes an orthonormality condition, which means that we restrict our search to all directions perpendicular to all previously selected directions, and we save this vector as P2. We repeat this procedure until m vectors are selected. The resulting ordered set of p's are the principal components. P1 will provide the direction along which the greatest variation in the dataset exists, P2 the next greatest variation, and so on. We can now describe the motion of the ball using only the significant PM vectors. We must choose which of the PM vectors is significant. In the current example, the magnitude of P1 will be much greater than the others because the ball only moves along the P1 direction. All other directions are noise. So how do we do PCA on an XRF image? Consider that we have collected a stack of images at the same location, but at several energies across the iron K edge. We turn the image into a matrix X that has n columns and m rows. N is the number of pixels in the map, and m is the number of energies. When we do PCA, we will generate m principal components, and these principal components will be a new set of maps that show the areas of greatest variation in the images. Let's look at an example in SMAC. So first, we're going to go ahead and open our data set. This is a multi-energy data set. We'll select the first energy, hit open. Okay, so we're actually looking at iron. This was a map collected at 7122 EV. Now that I've selected one energy, I'm going to go ahead, say rapid import from. I'm going to go and select all of my energies, 7122 EV, 7124, 7126, 7130, 7150 EV. Hit open. I want to select the iron channel because this is at the iron edge. Hit OK. Now you can see I have my new channels loaded. As I'm clicking through these channels, you can see that the signal, although the intensity gets brighter as we go across the iron edge, the pattern in intensity remains very similar across all energies. So this is an example where it's easy to see changes in intensity that are a function of the change in the iron concentration in this data set, but it's very hard to pick out whether any changes in these intensities is due to the presence of different chemical forms of iron, specifically iron 2 or iron 3 forms. So for this, we'd like to use PCA. Before we do PCA analysis, we should do two image processing steps first. First, we're going to right-click on this map and do edge removal. This removes any artifactual signal, usually dead pixels on the side of the screen. Secondly, we're going to go to Process and Advanced Filtering. Going to Blur. Select all of my iron channels to blur. Set my filter size to 5. My standard deviation to 0.8 and hit Save. And then Done. Blurring was covered in a different tutorial. For PCA, we like to blur because this helps remove some noise, which allows us to find the significant components in PCA more easily. In order to do the PCA, we simply click PCA Analysis. This pops up with a new window in which we can select our PCA channels. We'll select our blurred energies, and then we're going to simply hit SPCA. When complete, the vector plot view will pop up. The components, the principal components, are listed on the x-axis and their values on the y-axis. You can note that we have values that range from negative to positive. You also note that we have 5 components, and that's because we had 5 input energies. If we scroll down through the data channel list, you can see that we now have SPCA 1, 2, 3, 4, and 5 listed here. So let's scroll through these. The first component, PCA 1, looks a lot like the iron channels. This tells us that PCA component 1 is likely showing us changes in concentration that occur in this sample. That's not surprising. Typically, the greatest variation in an XRF image comes from having different concentrations of the element of interest present in the sample. And so this is typically what you see for component 1. Component 2, however, has distinct bright spots that are not observed in the iron energy channels. That means that these bright areas are likely areas where there are distinct chemical forms of iron present in the sample. And this also is typical. Usually we look for chemical differences in PCA component 2. PCA component 3, we get some bright spots. These actually overlap with bright spots in component 1, and again with bright spots that we see in the iron energy maps. Component 4 looks to be mostly noise, and component 5 looks to be mostly noise. So in this instance, we have either 2 or possibly 3 significant principal components. The last thing we should do in analyzing our principal components in SMAC is to multiply each principal component by -1. The reason we want to do this is because the display in SMAC only shows positive values. If you have a negative value, it will display that negative value as a 0. And as we said before, these principal components can and do have negative values. So to view all of these negative values instead of just viewing zeros, we need to go to Map Math, scroll down, we're going to select PCA component 2, multiply PCA component 2 by a scalar and make that scalar -1. Now I'm going to save this with a new name, neg PCA2, do the calculation, save the calculation. So now I can compare my neg PCA2 to my positive PCA2, and in this instance, it appears that neg PCA2 does not give much additional information beyond PCA component 1. So, in order to verify whether these spots in the image are actually distinct chemical species of iron, we'd like to do point Zanes analysis. So, when I collected this data set, I in fact selected points to do Zanes spectroscopy based on these PCA images. So I'm going to go ahead and load those parameters for where I selected my Zanes using the plot marker window. I'm going to go ahead and make these big empty circles so they're easier to see. Okay. And you can see that when I selected points to do Zanes, I selected 2 bright spots from component 2 because I think that these are going to be different forms of iron than the majority of iron that's present in the sample. I also, if I look at component 3, selected that bright spot in component 3 that's also present in component 1, and a bright spot in component 3 that actually is also a bright spot in component 2. Finally, my last Zanes data point was chosen based on component 1, and I chose something that was a moderate signal in 1, thinking that this would be a typical spectrum for the sample. So let's see how well I did. So again, this is PCA component 1, 2, and 3, and you can see where I selected my Zanes spectra. This plot here shows the Zanes spectra from those points that are selected, and you can see that I was in fact able to find different species of iron using this method. You can see that this first spectrum here is different from the second spectrum, and that these 2 spectra are different from the third and the fourth spectra that I collected. So in this instance, PCA was able to do a good job of helping me find distinct chemical forms of iron present in this sample. There are other tools besides PCA that we can use to look for chemical differences within XRF images. These include non-negative matrix factorization, NMF, and cluster analyses, Kmeans. So PCA is a common and robust way to examine variation in a dataset while minimizing redundancy, i.e. components that have overlapping information, due to the orthogonality constraint. However, the components can be hard to interpret because they do not have intrinsic chemical meaning. For instance, PCA components are often negative, even though XRF intensities never are. To obtain components that do hold chemical meaning, we can apply NMF instead. NMF yields a set of components that can be thought of as chemical end members. Alternatively, we could use clustering analyses which seek to categorize the pixels in the sample image into different groups according to how similar their spectra signals are. There are actually many types of clustering algorithms. In the following example, we will use an algorithm called Kmeans. So let's go back to our SMAC window. To do NMF or Kmeans, we'll go back to the PCA analysis. We'll select our channels as we did before. Going to select our blurred energies. And so now first I'll hit NMF to do the non-negative matrix factorization. Okay. Again, you'll get this line plot view where you get the NMF end members and their intensities. And you can see that they're all positive values. If you scroll down, you can see that we have component 1, 2, 3, 4, and 5. Unlike PCA, these are not ordered in terms of their significance. We can see that NMF component 1 is actually very similar to PCA component 1. 2 does not look like it has very much information in it. Component 3 looks a lot like our PCA component 2, has some distinct bright spots, and you can see that those bright spots are the same ones that I chose to do Zanes analysis on based on my PCA analysis. Finally, component 4 is fairly similar to component 3, not much extra information there, and component 5, not much extra information there. Based on the similarities between component 3 and PCA component 2, I suspect that I would have chosen the same set of Zanes points if I had used NMF instead of PCA to select spots for Zanes analysis. So you can see that NMF is an alternative to PCA. It does the same job in a different way. So the last type of statistical tool that we'll give an example of is K-means clustering. Again, we're going to go back to PCA, select our channels, and now hit K-means. Unlike NMF and PCA, where your end member number is going to correspond to the number of channels that you input into the analysis, you can choose the number of clusters when you do K-means analysis. It's wise to choose at least the same number of clusters as you have channels that you're doing the analysis on, and sometimes you actually even want to increase the number of clusters above the number of input channels. In this case, we're going to stick with 5 and hit OK. If you scroll down, we have just one channel. It's called K-means clusters. If we select it, you can see that different areas of the map are color-coded. Each different color corresponds to a different K-means cluster, and all pixels within each of the colors are more similar to each other than they are to pixels that are shaded a different color. So red pixels are similar, blue pixels are similar, orange pixels are similar, etc. You can see from this image that it would have been fairly difficult for me to select distinct Zanes points based on the K-means clustering algorithm. In this particular sample, I would have liked to rely on either NMF or PCA. However, K-means clustering can still show me that there are changes in signal intensity across the sample. And I may be able to get useful information out of knowing that there are these different clusters of pixels where the signal is more similar to the other pixels in that cluster than to pixels from another cluster. So that concludes our tutorial on statistical tools for image analysis. There is one additional tool, simplex volume maximization, that is covered in a separate tutorial.